If you recall your knowledge of the motion in one dimension together with that of vectors, you can understand the motion in two dimensions. By knowing the definition of position in one dimension and that of displacement as well, and generalizing this definition into two dimensions as a vector, we can fully understand and define the displacement and position in two dimensions. From this knowledge, we can use it to define the average and instantaneous velocity as well. Moreover, the average and instantaneous acceleration can also be defined, and then we can also demonstrate the two-dimensional motion with a constant acceleration. The applications in this can be demonstrated in projectile motion and also in circular motion, in addition to that of relative velocity. The emphasis will be made in this session on projectile motion and circular motion. Starting with the definition in one dimension, and knowing that the particle moving along the x-axis can have a position and a displacement, and also may have a velocity and an acceleration. From this definition, also we can understand from this picture the motion in two dimensions as shown now, and then the definition of position in two dimensions may be understood by having two motions, one along the x-axis and the other along the y-axis. And if you combine these two motions, you're going to get, for example, a definition for the position in two dimensions. So we have here one along the x-axis, motion along the x-axis, so a position along the x-axis, and another along the y-axis. Or it can be understood in a different way. If you have a vector in two dimensions, so you have two components, one along the x-axis and the other along the y-axis. Similarly, for the velocity might have two components in both directions, and also that for the acceleration. As you notice here, the position and the velocity together with the acceleration are all functions of time. However, in 3 dimensions, these variables can be represented in terms of the 3 unit vectors I hat, j hat, and k hat, where k hat is the unit vector along the z-axis. So we have these 3 definitions. As you know, all these vectors must have directions and magnitude. In one dimension, as we explained before, the position may have a magnitude towards the positive x-axis or a magnitude towards the negative x direction. In either cases, its displacement is taken as the difference between the final and the initial position. For instance, if a particle at the beginning of its motion is at a position -3, and then it changes its direction and becomes at a position of 1 to the east. In this case, the displacement is going to be the final position, which is this one, which is equal to +1 minus the initial position minus this one, and you're going to get a displacement of plus 4, and that is towards the positive x-axis. This is the way we used to define the displacement in one dimension. We can use this definition to generalize the motion in two dimensions, as the particle might have initial position in here and a final position in here. As you can notice that the initial position might have two components, x component and y component, and the final position as well has two components. So by taking the difference r final minus r initial, you will get the definition for displacement. And this definition may be represented as a delta x, a change along the x-axis. That's the displacement along the x-axis, and a displacement along the y-axis. Obviously, the presence of unit vectors I hat and j hat will never ever allow us to add the number of delta x to that number of delta y, because they are both independent of each other. Now, to understand the average velocity, let us put the general definition we had before, that the average velocity is the change in position divided by the time interval. Considering that delta r is equal to delta x plus delta y, delta x I hat plus delta y j hat, and dividing that by delta t, we're going to get two components. The first one is delta x over delta t, that is the average velocity along the x-axis, and delta y over delta t, that is the average velocity along the y-axis. Now, to define the instantaneous velocity in two dimensions, we're going to take the general definition of the average of the instantaneous velocity, that is the derivative of position vector with respect to t. Now, by defining the position vector as having two components, x and y, that is r as a vector, we used to define it as x I hat plus y j hat, where it has two components, as we said before. By taking the derivative with respect to time of this, we're going to have also one component called bx along the x-axis, and another component of velocity along the y-axis called v sub y. Each of these vectors, r or v average, must have a magnitude and direction. However, if a position vector of this position is defined in here by having two components, x and y, the velocity vector is usually drawn tangent to the path of the object, as shown in this figure, where v at this point has two components, vx and vy. As you can see, if the component is if the velocity vector becomes in here, in this case the velocity vector change its direction, even if and maybe its magnitude as well, then in this case we have an x component and a y component which is different from the previous one. This is the way we define the velocity, and we can find also its magnitude and direction at each instant on this curve. Also, we can find the position of the position vector at any time on this curve. This is a simple example to demonstrate the motion of a turtle, and the turtle in this example is moving with a constant velocity of magnitude 10 centimeter per second in a direction of 25 degrees with respect to the x-axis. We can have this simple example to determine the coordinates of the turtle 10 seconds later of its motion. And also we can find the distance by which this turtle walks in the 10 seconds. Now, if you look at the diagram, the turtle moved a distance, or it is at a position d from the origin as a vector, and this d is nothing more than the magnitude of the velocity by the time, because the speed here is constant and the angle is constant, so the velocity of the turtle is considered as a constant. To get the position here, you just simply multiplied to get the magnitude of the position, you just simply multiply the magnitude of the velocity by time. Then you can get the position at magnitude of the position at 10 seconds. And also you can have its component. If you project this along the x-axis, you get the x component, and if you project this position along the y-axis, you get the y component. To do that, also we can get the velocity vector or the two components of velocity vector as well, as long as this velocity vector is constant all the way. So simply we can have two components, v cosine theta as vx and v sine theta as vy. As you know, always in a triangle like this one, you have to know that the side closest to the angle, always it's nothing more than the product of the magnitude of the velocity by cosine theta, while the one opposite to the angle, like this one or this one if you like, it is v by sine theta. So in this case, as long as the velocity is constant all the way, because the slope of this one is constant of this path, so you're going to get obviously the same components all the way, which means that the velocity is constant in magnitude and direction. And here we're going to have the simple answer. The x motion, we have Vx. By substituting the values, we're going to get the x component as almost 9 centimeter per second, while the displacement is just the product, as we said, the velocity by t, and here delta x is the same as d defined in the beginning. So we're going to get that equal to 90.6 by multiplying the magnitude of the velocity by the time of 10 seconds. Also, the y component is nothing more than the magnitude of the velocity by sine the angle. And if you put all these values in this equation, you're going to get 4.23 centimeter per second. Similarly, for the displacement along the y-axis, it is the product of the y component by the time, and that is 42.3. If you want to find the magnitude of the displacement, or the position, if you like, from the origin, displacement or position from the origin is almost the same, you're going to have to apply the Pythagorean theorem by squaring the delta x and squaring delta y and add them together and take the square root. So the answer is 100 centimeter. This is one of the simplest examples for motion with a constant velocity. In order to find the average acceleration and scientific acceleration, let's define the average acceleration in its general form as the change in velocity vector divided by the time interval. To find the change in the velocity vector, we have to get the final velocity and initial velocity that corresponds to the final time and initial time. Simply by substituting the relation of the velocity vector as Vx final into an initial, and then take or divide the results by delta t, we're going to get two components for the acceleration, that is delta Vx by delta t, that is the average acceleration along the x-axis, and delta Vy by delta t, that is the average acceleration along the y-axis. And to define the instantaneous acceleration, the definition in the general form is the derivative of the velocity vector mentioned here with respect to time. If you take this derivative, also you're going to get two components, ax along the x-axis, the acceleration ax, which is the derivative of v sub x by dt, and also a sub y, which is the derivative of v sub y by dt. So in this case, the acceleration vector obviously at each instance of the path will have a magnitude and direction, and it might change from point to point. It must be remembered here that the velocity vector may change when change just its direction, or just its magnitude, or it change as well when both magnitude and direction change. And also one more point we have to mention, that the acceleration and velocity and the position in 2 dimensions will have different directions. Each one may have a certain angle with respect to the horizontal, different from the first one. To summarize the motion in 2 dimensions, the position vector may be defined as r equal x I hat plus y j hat. The average acceleration is simply delta r over delta t, which constitutes of two components, one along the x-axis, that is delta x over delta t, called v average along the axis x sub x, and the other one is delta y by delta t, that's the average acceleration along the y-axis. And the instantaneous velocity is defined along the x-axis as derivative of the position x with respect to time, while the velocity component along the y-axis is derivative of the position along the y-axis y divided by t. And the velocity vector then in general is nothing more than vx I hat plus vy j hat, that is the derivative of x with respect to t accompanied with I hat, and the derivative of y with respect to t accompanied with j hat, which indicates again there are two motions, one along the x-axis and the other along the y-axis, and they are combined in terms of these unit vectors. Again, the acceleration is along the x-axis is defined as the derivative of the velocity component along the x-axis with respect to time, or the second derivative of the position x along the x-axis with respect to time. Similarly, the y component is the derivative of the velocity component with respect to t, or the second derivative of the position y with respect to t. Then the acceleration has two components as well, instantaneous velocity acceleration along the x-axis, ax, that is dvx by dt, and ay, that is dvy by dt. It must be remembered that the position vector and the velocity vector and the acceleration vector are all describe the motion in 2 dimensions, and they are all a function of time.